YouTube introduction series with R, and this is the first of a three-part series. I'm not sure what parts 2 and 3 are going to hold yet, but
I did get somebody to do Python for July.
oh, sweet.
Yeah.
I like
Joel Caddy is going to do Python.
Awesome.
Should be pretty
We
good.
got Python coming up, and I think you were going to do Tableau at some
Yeah,
point.
we're going to try to get somebody to do visualization in like D3 in August, and I'm going to do Tableau in August. So
Awesome.
that's the current plan.
I'd be interested in D3 as well.
Just got to find somebody that knows how to use it.
I see it all the time, but I've always been scared of it. So, I have some goals here. So this is kind of where we're going. This talk will take about an hour to an hour, 15 minutes probably. But feel free to interrupt me with questions if you don't understand something. The goal is to get you up and running with R. And so I had to make some assumptions. So I want to bring you from ground zero to analyzing data with R as fast as possible. Well, ground zero may not be exactly it, but hopefully you have access to a computer and have some background programming, understand some ideas of procedural programming. We'll encounter those in here, set for and if statements and things like that. You'll see those. Some motivation to learn. Unfortunately, we don't have a lot of time. So, when preparing this, I looked on YouTube and I saw some very good introduction to data science with R tutorials. They take the length of this talk and turn it into a 5-part series. So 5 hours instead of 1. So this is very ambitious. So I will gloss over a lot of details. If there are things in there you think you know R and you think I should point them out, it's probably a valid point. We already went over where to get R. We're using R in our studio, and the reason is R, I believe, is kind of clunky to use on its own. I like RStudio a lot. Previously, I liked Emacs for R, and there are a lot of other tools, so it's not the only one. But RStudio is popular with the cool kids, so they're going to use it. Packages. I want to talk about packages a little bit here. Part of the power of R is it is open source. It is extensible through the package interface. We're using 2 in here called dplyr and ggplot2, but there are nearly 9,000 packages right now that are official, and a lot more that are unofficial. If you are a hacker and you are brave and you want to go onto GitHub and download those and install those, more power to you. I do that on occasion, but it is tricky sometimes. But on the official R page called CRAN, C-R-A-N, they have a number of official packages which you can install very easily using install packages. Or you can use, let's see, I'm gonna exit out of this right quick. If you're in RStudio, it's even easier because you can just click on this install. If you know what package you want, say dplyr, assuming I can spell, even if I can't, it suggests the packages. So I've already done this, so I'm not going to go ahead and commit to the install, but package interface is very easy to use for the official packages. There are kind of two kinds of packages. General use packages like dplyr, ggplot2, or hmis, and are kind of general use and are just kind of things you almost always load. There are a lot more that are specialist packages for people in finance, for people in biomedical fields, doing group sequential designs with X, Y, and Z, and this. They can get very specific. So, part of the power bar is package interface. If you're doing a weird statistical analysis, there is probably an R package for it now. But we'll stick with dply or ggplot2, and I was going to use reader, but that's one of those details I'm glossing over. Second thing that is wonderful about R is you can get information everywhere. Well, it's good and bad because you can get an information deluge and just be awash and honestly get analysis paralysis. But help is very robust in R. I will demonstrate a little bit of that. There are many ways of getting help. All the commands have technical details. They have examples. They have options. And some of the packages come with this kind of documentation called a vignette, which shows you use cases. So you can actually copy and paste code from vignettes maybe and really have a leg up on your analysis or whatever you're trying to do. The book business for R use is booming. It has been for years. You could probably bankrupt yourself buying books for R. I don't recommend going down that road necessarily, but there's some high quality documentation out there published on Amazon Kindle, wherever. Cross-validated is a help site for all sorts of things, Java, JavaScript, whatever you want. Well, cross-validated is part of the Stack Exchange system, which is got help for everything under the sun, and they have an R tag. Chances are, if you come across an error or something weird, or just want to know how to do something off the wall, chances are it's been answered on cross-validated, or someone will know how to do it on cross-validated. There's also an aggregate of our bloggers. I have to put in a plug for that because they pull in some of my information sometimes. So, that's it for the slides. Don't want to take up too much time. Let's get to the good stuff. So, I talked about getting help in R. So, data frame is one of the central things in R. So, I decided to demonstrate getting help on data frames. So, I have this question mark data frame, and I just executed that command down here, and up pops the help in this section in the help tab. If you're following along in RStudio, the help tab actually probably popped up, and we're not going to go through all of this, but you can see all sorts of different references, some simple examples. You can copy and paste this code. You can actually run this code by typing in the examples command, but details glossed over. There are some related commands that you might want to look at, and you can see that here in the C also. So really a lot of information here. You can also use the help command instead of the question mark if you like typing more. If you don't know what command you're looking for, well, there's some help there too. You can do this help search command. Say, I know I'm looking for data frames. I need to find some information on it, so I do help search data frame, and this is going to think for a second. And then it's going to come up with all sorts of things that you can look at here. And again, we don't need to go through it, but these are all sorts of things that reference data frames. Here's the basic command. Here's how to convert a data frame to a numeric matrix. Everything you could want to know. If you know how to partially spell a command, you can do this apropos command. And again, this time it just comes up with a list of commands that have data.fr in them, including all of the data frame commands. So even if you don't know exactly what you're looking for, you can still probably find it. So there's a lot in here. R has a very strong documentation system, and they try to make it easy to document so that people will actually do it, and they've taken advantage of it. So that's where to find information. Let's get started in actually doing stuff in R. So as I said, we're going from ground zero. This is the basics. Assigning a number to a variable, 2 to A. So there it is, A is 2. We can use it as a basic calculator. 2 plus 2 is 4, 3 plus A is 5. Nothing surprising there. So it looks, almost like C, except for this weird assignment. You can use the equals command as well. I use this kind of arrow operator, really out of habit, I guess. They're almost equal, and I think there's some weird scoping issues with one or the other. You can do strings. There we assign foo to B, and we can retrieve it. We can also do any sort of string commands, again, glossing over details. Dates and times do exist. You need to know about it. It's a good thing to learn about it, but we don't have a lot of time here to go over that. But here you can see that there is a time difference, just to show you that there is a facility for actually working with this. Trying to plot the dates is a pain, but it can be done, and you can make some good time-based graphics. And the other reason I bring this up is because if you get into R and you're coding algorithms and things like complexity and running time are meaningful to you, there are some facilities in there that we really won't go through. Booleans, we do have true and false. They exist. In fact, we can do, we can bring those back up. And they do exactly what you'd expect them to in other languages. And then if you need to clean up, we have this rm command. You might recognize this as removed from Unix or Linux. And so after we execute this, remember we assign A to 2, well, now it is assigned. So this really looks like other languages so far. So vectors, now we're starting to get into the power of R a little bit. So vectors are a collection of objects of the same type. So whereas before we assigned a single number to A, now we have a vector of numbers, 1 through 5 specifically. Let's assign another vector because I want to show you that you can add the two vectors together. I just had a thought. Maybe next time. I thought I would actually enlarge that, but we'll do that next time. So you can add vectors together. C equals A plus B. And so what you get is element-wise addition, exactly as you would expect from your adding matrices in your advanced math class. You can add a scalar to a vector. So we're going to go back to A. Remember that A was 1 through 5. We're going to add 1 to that vector. And as it turns out, adding 1 to that vector adds 1 to every element in that vector. So now we have 2 through 6. So really basic stuff. It kind of behaves intuitively, I think. but this is very powerful. So with vectors, you have subscripting, and our subscripting is done with square brackets. So the third element of A is 3 as we'd expect, and we get that by doing 3 in square brackets. We can subscript A but assign it. So let's assign 18 to the third element of A, and it behaves as expected. Take that back to normal. We can, if you've used MATLAB or some of the other, I think Python definitely does this, you can pull out a subvector. So the first 2 elements. If you want to chop off the first element of A, there we go. We put -1 in the square brackets, and we return A without its first element. We can return A without its second element, so that's 1, 3, 4, 5, and we took out 2. We can remove more than 1 element, so all sorts of combinations, and you can take these ideas and do some pretty sophisticated things. So what is this 1:2? I want to show you, it's a shorthand for a vector. So A.1, I did 1:5, and that gives you 1 through 5. So a colon is one way to give you a basic sequence that increments by 1 every time. So 1:5 is 1, 2, 3, 4, 5. 2 through 10 gives you 2 up through 10. So vectors can be done with strings as well. And again, glossing over details, there are all sorts of functions that operate on vectors of strings. Lists are more flexible than vectors. I don't want to go through lists too much, but you can think of them as associative arrays, named collections, or some of the other things I've heard. And if you do a list like that, you'll get back a notation like this. You can see that these are very different structures that I've assigned to this list. This may not be the best use of a list, but you can access elements with this dollar notation, or the same thing with 2 square brackets if you want to go by position. And then, again, I'm doing the same thing here using the dollar notation for the third element, or looking at the double square bracket. So lists we're not going to do much with except until we get to data frames.
And the main difference between the list and the vector is vector has to be all the same type or class.
Vector has to be all the same type. By the way, there are named vectors. You can put names to them and make them act like associative arrays as well. And sometimes you want to do that, but lists are the main time where I've seen that done. So flow control, this is where I assume you've been in some sort of, or familiar with some sort of other language, C or Java, or this really looks like your basic. If you like Perl, this looks like Perl as well. We do for I in C234, so that cycles I over 234. And I decided here to print, why did that oh. That's why that didn't happen. I promise I did test most of this before I came here. All right, so there I printed I and A subscript I together, and you can see 2, 3, and 4. But I hardly ever recommend the use of the for construct in R. And the reason is because there is an example or a quality of R that you have seen already in this talk, but we haven't talked about it. There is usually an easier way to do something instead of a for, using implied loops or vectorization. So in this case, we could have just done a fancy subscript. Here we could do a fancy subscript. So instead of doing, well, let me actually run this code. Why not? I'm going to run all of this code. For I in 2 to 4, add 1. So there's 1, 3, 4, and 5, and 5. But that is, in R, is a silly thing to do because we can do our fancy subscripting. So we can just use a to the 4 equals a to the 4 plus 1 and accomplish the same thing. So the lesson here being, there's this implied looping in R that almost, but not always, makes the for construct obsolete. So if we wanted to print out every element of A that is greater than 3, we have any elements made that are not calculated. So this will actually show something interesting. So that is a for loop that prints out everything that is an A that is greater than 3. So for if, but we can do some fancy subscripting here. And notice I did a subscript here of A greater than 3. So I took the name of the vector A and I said I want the elements that are greater than 3, and then I put that in a subscript. Again, we accomplish the same thing without a for loop. This is all implied. R does the looping for you. So that is one of its powers. We don't need to use the same elements or the same vector in a subscript. Here I said print out A in cases where B is greater than 6. So let's remind ourselves of A and B. A and B. So and B is greater than 6 in the last, greater than or equal to 6 in the last 3 elements. So we would expect to see the last 3 elements of A here, and we do. So why is this? So we can do these comparisons. Again, it looks like C or Java. And this is returning a vector of Booleans. So with Booleans, you hardly ever assign a variable as true or false. You usually get those through these comparisons. B is greater than or equal to 6, or A is not equal to 3, or whatever. So, so I took this, the same vector Booleans, and I put it in manually into as a subscript of A, and you get the same thing. So that's kind of what's going on there. Pretty powerful stuff. Looks deceptively simple, and that's probably the power of this. So, factors. So I haven't gone through factors yet. They're a type just like numbers and strings, but I wanted to save them for this part because they are more powerful as vectors. So we're going to assign a very silly looking vector. It's 1, 2 repeated 3 times. So 1, 2, 1, 2, 1, 2, 4 times, sorry. So we got this, weird looking vector, but this is something that often arises in, say, design of experiments or some other statistical context. So we're going to assign a new variable, g.1, as factors, and we're going to label this as low and high. So now you see g as a whole bunch of 1s and 2s. That's kind of hard to read. And you see g.1 as low, high, low, high, low, high. This might be a setting on machine or temperature or something like that. That's factors. With covering functions, I went back and forth on this. Functions are a very important part of R. And they act just as you would in any other language. I designed a simple function here. It takes 2 variables in x and y and gives a default value of 1 to y. And it just returns their sum. And so there are a lot of things you can do with this. If I called it with just a single variable, it returns that plus 1. I'm doing the same thing here, but assigning x explicitly, and that's the first variable. I'm calling this with 2 variables, or 2 parameters now, and it returns the sum. Again, we're returning the sum of them up here. I'm doing the same thing, except I'm naming y. And now I'm trying to do this by naming y, but I leave out x, and it gives you an error. So it really it's kind of like in C++ in this respect. So functions do behave the same way as in most other languages, but you can assign default values, and there are some other powerful things in there, like flexible parameter lists that I don't want to go through. But I just wanted to tell you that functions do exist. They're enormously important. They're your building blocks, but time is going to be an issue right now. So we're going to clean up. And I wanted to notice this time that I didn't clean up x and y. Oh, yeah, that's fine. I didn't clean up x and y because variables and scoping, variable x and y only exist in this function and don't exist out of it, which is what we'd expect if you're coming from another language. So, this is a whole bunch of contrived examples just to show you the basics of how vectors and different numbers and strings work. Are there any questions so far? Next, we're going to get into something a little bit more interesting. So, simple aggregated statistics. This is where we start getting into some data analysis, and I wanted to get here as fast as I could to give you something. So, first of all, R has many ways to create structured vectors. So instead of doing this 1, 2, 1, 2, 1, 2 business, I'm going to create the same kind of vector. And the reason we do this is because in designed experiments and in many other cases, there's reasons to easily create these structured vectors. So I have an easier way using the rep command. And if you wanted to get help on rep in RStudio, you click on it, and then I am hitting the F1 button, and it comes with the help. And so I wanted to show you that exists. Now, as you probably expect, we want to create a factor out of that. Usually with structured vectors with very few numbers, I would want to create a factor out of it. I'm going to create some data. And again, this R norm is creating random normal variables. And again, you can hit mouse over it, hit F1, and get everything you ever wanted to know about this command. So we're going to leave group behind for a second and show you the mean command that gives you the average of data and the standard deviation. Now, if you're coming from a statistics class, you might notice that mean doesn't really mean a lot in this context because I defined it by adding group, which is not really, it's not a zero variable. So, because we believe that group has an effect on that, we might want to apply basic statistics by group, and we do that using this tapply command. And yes, I'm skipping over all the other apply commands for right now. So, we do this tapply. The data we want to analyze, our grouping data, our grouping variable is group.fact, and then the summary we want to do. So here we want the average, and so this says for data, we want, or for dat, we want to group it by this group.fact, so this low high business, and we want to take the mean over each group, and that's what we get. So we get a vector out of this that says low, and we get the mean of the low group and high. And so is this something we expect? And the answer is yes, because we added group and we subtracted 1. So we added 1, 2, 1, 2, and then subtracted 1 from all of those. So we'd expect high to be, the high group to have a higher mean than the low group. This might be some strange data that I got because I didn't set the seed for the random number generator, but we do get a higher low group. We can do the same thing with the standard deviation. So tapply, the data we want to analyze, the grouping factor, and then standard deviation is SD. So again, this is the second basic statistic we did up here, but we were grouping them by this grouping factor. And we really did get some strange data here because I actually expected these to be the same, not off by a factor of 3, but you know, that's what we get for doing random numbers in the middle of a talk.
So can you do more than one group? Can you nest them in that command?
Can we nest them? I don't think there is nesting that can be done.
Because like in Excel, it's kind of analogous to like a pivot
Yeah.
table and then a sum or a average or whatever.
For tapply, you'd really have to create a kind of a cross product variable and do it that way. And by the way, if you were looking at the comments, I did call this the hard way.
Before declare.
Before dplyr. So all of this is basic R, vanilla R. Actually, it is the S language, but as implemented in R. Base R is hard sometimes, and I'll put it that way, but it is very powerful. And it is geared toward data analysis with commands like tapply. There are other commands that in base R that do it, but I think they're so clunky and I like dplyr so much, I'm going to show you dplyr later on. Before we get to dplyr though, we got one last thing we got to cover, and this is probably the most important structure for data analysis, which is the data frame. So now we're getting into a level of sophistication that's really going to allow us to think of data in terms of a data set as opposed to a bunch of numbers strung together. So vectors, a bunch of numbers, or a bunch of strings strung together. Now we're getting into structures that help us think in terms of data sets. And I'm going to use a built-in, probably at my peril, use a built-in data set. There are ways of importing data in R, and I made the decision to gloss over those details. So we are using the Iris data set. This is a very famous data set that appears everywhere. It has been analyzed to death, and we're going to continue to analyze it to death. So this is what the Iris data set looks like. If we just show it as a data frame, it's a massive, or not massive, it's 150 observations, it's not massive, but it took up a lot of room here. In both R and R Studio, you can do this view command on a data frame. Notice the view command has a capital V, I don't know why, but now this brings this up in our spreadsheet. There is some power in this spreadsheet that has come along recently. You can sort. So SQL length, I just sorted this by SQL length. So the records now are sorted in ascending SQL length or descending SQL length. We can sort by species. We can even filter. So there's a bit you can do in here. It acts a little bit like Excel in this way. So some of the things the data analysis that you think about doing if you're doing it in Excel or I guess OpenCalc, if that's your thing, you can do here too. You can set ranges here if you wanted to. And there is actually a lot of value into doing data analysis just by filtering and sorting. So, I mean, don't skip over this like I am here. This might be worth time to actually look at. So, what is this? What is this data frame object? And it turns out, so I just using this str command, I just exposed the underlying structure of this. This is a list of vectors. So vector has to have the same kind of observation in each slot, but a data frame can have different kinds of variables in one single data frame. So you can see we have 4 numeric vectors and 1 factor vector. So that's helpful. This kind of leads you to think that we might be able to group this data frame by these species. And you will see very soon that we will do exactly that. But before we get there, let's go to some of the base R operations. This head will show you the first few observations, the first 6 in fact. You can change that, I guess, if you want to see the first 10, you can do count 10 and get the first 10. I do that a lot. This is a surprisingly useful command. Just what does this look like on paper? Same as the view, but this is quick, and sometimes it's just nice to see things laid out. This summary command, actually summary works on a lot of stuff, but it works very nicely on data frames. This gives you summary statistics, minimum, first quartile, median, mean, third quartile, and maximum. Very handy. Just get an idea, a basic idea of what your data is. So this is a very useful data analysis tool, the summary command. Of course, I chose the Iris data set because summary does not spit all over the page with thousands and thousands of variables. So maybe this is one of the nicer examples, but it is still surprisingly useful. You can subscript a data frame just as you do a vector, but this time you use 2 dimensions. So in this case, I am pulling something from the 35th row and the first column. And 4.9, so if we go back, I got rid of the view. So what do we do? The 35th row, first column. The 35th row and first column is 4.9, and we got 4.9. So what if I did 35 comma and then nothing? So this is, I know Python does this. I know SysIML does. I think MATLAB has something like this. But this just shows you the whole row. So this is the 35th row. Let me go back. 35th row. And we can see that it matches up. We can do the same thing with the column. So we can pull in the first column. And so this actually returns a vector that represents the first column of this data frame. That first column happens to be called sepal length. And so here is this dollar notation. Because a data frame is actually a list, we can use the dollar, and it pulls the same thing. I use this dollar notation a lot. And I want to show you something. In RStudio, when you do the dollar notation, they actually have some support here for this. So you can see this list of variables as soon as you type in iris dollar. And it saves you a little bit of time. It lets you know what variables are in there. You can use the arrow keys and then run it. And so actually that's a hidden thing in RStudio. It's not in the base R. If you wanted to, you can use the double bracket notation to get the first column. This is actually the first time I've ever seen this done, so your mileage may vary. As I mentioned, if you pull a variable out of a data frame, it is a vector. You can treat it like a vector and subscript it. You can get the mean of it by doing mean and then the name of it. I call this basic exploration the hard way. If you want to get the correlation between 2 columns, you can again use the core command. It's part of base R, and you can do you can type in these variable names by hand. I call it the hard way because this is kind of a kludgy notation, but you can do it. There is actually an easier way if you want to. So here's where I get really fancy with the subscripting. I don't put in anything for the row. I put in this 1:4 for the column. So that recall earlier, this is 1, 2, 3, and 4. So 1, 2, 3, 4. So we're getting correlation of all 4 columns. So what does this do? This gives us a correlation matrix with all 4 of those variables. So that's kind of nice. So you're trying to do some data analysis. You look at this correlation matrix, which I do recommend in many cases. You see pedal length and pedal width have a very high correlation. Pedal length with pedal width is 0.96 correlation. So if you're trying to do some predictive modeling and you put in pedal length and pedal width into your model, you might have some problems if you remember from your linear model statistics class. We can use tapply with these as well. I mean, they are, after all, just vectors. So this time, my data is sepal width. My grouping, remember the species is a factor, and we're gonna do a mean. So here we're looking at sepal width. So if we're finding that a sepal width has a higher mean in the Setosa species than the others. We can do the same thing with standard deviation. So really breaking down these means, so we're starting to get some insight into maybe the differences, some of the differences of these species. I wanted to mention that functions work on data frames too. So I have this add one to call one. It takes a data frame as an argument, and it takes the first column and adds one to everything in it. And then it returns the data frame. So let's run this. And the reason we have functions that work on data frames, later on when we get to dplyr, we want functions that work on data frames. So I defined this iris2 as add one to call one iris. And so let's just look at this, look at what I did here. You can see the width, the petal length and the petal width and the species are unchanged, but sepal length in the second data frame is exactly one more in every case than the sepal length. So it's kind of nice to have functions that can work on, manipulate data frames. And as you get into more data analysis, you'll find that you'll be writing these functions kind of on an ad hoc basis to do some specific analysis on data frames, and we'll see that. So, any questions on data frames before we head into the better stuff? So, really, I'm doing just doing a drive-by shooting on R here. So, again, data frames, they're kind of the central character. There have been improvements to data frames in R using different packages, but really data frames remain essential. I haven't really used those improvements a lot. I've checked them out. So dplyr, data analysis with dplyr. So dplyr is kind of an evolution into how we manipulate data in R. So used to manipulating data in R, we had commands that do this kind of apply by group. We call it split, apply, combine. It was really kludgy until Hadley Wickham came along and wrote plyr, and then he wrote dplyr as a successor. And it really changed the way we started thinking about doing data analysis in R. And this is why I wanted to get to dplyr. So if you look at this code looks a lot different from what we have seen in other in the previous part of this demo. We've got this command, and if you've used the Unix or MS-DOS, you might recognize this as the pipe command, and it works exactly the same way. So we're taking data, we are piping it to another command, and we can string these pipes along forever if we wanted to. And really, this is kind of a revolution. The second part of dplyr is we really break down the steps of data analysis. So think of things you can do to data frames. You can subset them, you can split them apart, you can put them back together. You can create new columns, you can chop off columns, you can rename columns, you can summarize data. So dplyr really took those different steps and wrote specific functions that did those steps really well, and then you string them together with these pipe commands. So, to me, if you're writing in C or Java, a lot of times you're thinking in terms of what is the running time of this program? What is the CPU time? Well, dplyr takes a little bit of a different tack. Yes, it is written to be optimized. There's a lot of it that's written in C++. But it is designed to reduce the burden on your brain. So you're thinking about data analysis rather than writing code. So let's get started with dplyr. So we load dplyr up. So that's the first part of this. I probably already did this. It's one of the first packages I'll load up when I ever use R anyway. So,
Quick question, I
Yep.
missed the beginning. Did you have to install the package dplyr?
yes, yes, you have to install the package dplyr. And I recommend it anyway. It is a general use package. There are a whole bunch of sister packages that go along with it that I'm not covering here, but it is worthwhile to do. So I want to create a variable called this mean stat all. So mean stat all, if you take the hint, is the mean statistics for all variables. Okay, so I want to get the mean of all variables in this data set. We are going to leave out species for now because it is a factor, and taking the mean of a factor is just a silly thing to think about. So first of all, I mentioned the data set. Then I'm going to pipe this data set into this summarize command. Hadley Wickham is from New Zealand, and so we get summarize spelled with an S and not a Z, but you know, I used the summarize command with a Z once, and it didn't work. So I've used the British spelling ever since.
I heard they updated that.
I-
I don't remember.
He probably did. Now I'm a creature of habit, so
Yeah.
when I'm in dplyr, I'm thinking British spelling. So n equals, so we do the summarize command equals n. This gives a count of the number of observations. Then I do this mean sepal width equals the mean of sepal width. Mean sepal length. So I just keep on assigning these new variables equal to mean of sepal length. SD of sepal width. Okay, so I lied. These are not all means. Some of them are standard deviations. But what I'm doing is I'm saying I want a summary over all of this data of these different variables. So let's execute this and see what this looks like. So we get a data frame. Actually, it's Hadley Wickham's evolution of a data frame, which doesn't make a lot of sense to me, but there you go. It's essentially a data frame with some slight changes. So I get this, everything I assign here, n equals n. So n is 150. This 150 comes from what? The number of rows in the data set. So that is this n command. Mean sepal width, you see that down here. And this is the mean over all of the variables in sepal width. Mean sepal length, again, the mean over all of the data points of sepal length. SD sepal width, this is the standard deviation over the whole data set of sepal width. And again, for SD sepal length. So this command is not very hard once you get used to dplyr, and yet we got 4 summary statistics out of this. If we had done this with tapply, it would have been a little bit more of a pain. Okay, so that's nice. We got a summary over the whole data set, but we saw earlier that we think the species might have something to do with the sepal length and width. So let's, I want to point out, this new command is almost exactly the same command as the older command. with the exception that I changed the variable name and I added this group by species. So instead of piping iris straight to the summarize command, I'm piping that to this group by species, and that does exactly what you expect. It breaks down everything by species before it does the next step. And that next step is summarizing. So let's actually execute this. So we get a data frame with 3 rows, and those 3 rows are indexed by species. So Setosa, versicolor, virginic. I believe I said those correctly. So this N, as we said, is the number of rows. Each one has 50. And if you want to actually count, this is split by species, or sorted on species. So we see that the first 50 rows are Setosa. Up to 100, we get versicolor, and then the rest are virginic. So that checks out. And we get the mean of the SQL width. And we already did this, right? We did the SQL width earlier, I believe, with the tapply. But you can actually go by, if you're taking this home and downloading the text code, which is on GitHub, so you can grab it. You'll actually find that these are the same values. So, but it's a completely different mindset. Here, the data frame of the data set is the center of our data analysis. We group, we're splitting off thinking about grouping from the summarizing. So we've really pulled those 2 steps out. Okay, that's not all we can do. We can define a new variable. So I do that here. I do this almost the exact same thing. I pipe this to this mutate command. It does not create alias. It just defines a new variable. We named that new variable SQL area, and you'll see why in a minute. And I call it SQL length times SQL width. So this is, I defined a variable that basically takes the bounding box of the SQL and computes its area. Just for an example, I don't know if this is a biologically useful thing to do or not. Just to show. So I created this new variable. I began group by species because I'm suspecting species is an important issue here. And then I summarize my new variable, SQL area, and give it standard deviation. So let's do it. And here we see that species may in fact be an important factor on this length times width vector as well. Is it worth doing this in a predictive analysis? I mean, we're not covering that here, but this kind of analysis and this kind of exploration can help you answer that. Very good for feature. I'm blanking on the name. Feature engineering. All right. We can do some more. We can filter. Filter means subset. Filter is dplyr speak for subset. It is also RStudio speak for subset. So I clicked on a filter command up here to do subsetting earlier, and I do that here. So let's say, for the fun of it, well, for argument's sake, for right now, let us say that we have prior biological knowledge that if the SQL length of this flower is 7 or higher, then the species must be virginica. So if we have a flower that has A 7.0 or higher sepal length in a species is not Virginica, then somebody did something wrong. They measured wrong, they have a typo, they looked at the wrong flower while they were entering data or whatever. So let's look at this. I actually did this for a reason. So if we do this, we are going to toss out this record here, this 7.0. So I actually looked at this data set when coming up with this extremely arbitrary condition, just for illustration. We can filter that out, and that just means adding a command into what we did before. So very same command, except we add this filter in, and I put in a logical condition, this OR condition, and either has to be less than or equal to 6.9, or it has to be Virginica. So kind of thinking in terms of programming language here. So we can't abolish the thinking of coding altogether, but we can do a lot of that. We group and we summarize. And we do that, and you can see that one record for Versicolor got tossed out. There are only 49 records. It really didn't make much of a difference here, honestly, but for sake of illustration, that's what we're able to do. So if you need to exclude outliers from your analysis, filter is the way to do that. And then I'm not going to explain this. Dplyr is a different way of thinking from the rest of R. Sometimes that gets a little bit ugly, so we do this do command. We did a correlation matrix on this earlier, and I just want to show you that it is possible to do a correlation matrix that is grouped using this do command with this strange notation. So dplyr can play nicely with base R, but you gotta hack it together. Probably a detail I didn't need to share, but I did do a correlation matrix earlier, and I wanted to show you that it is possible to group that. Okay, questions before I go into ggplot2.
Are there any nice ways to do that?
Huh?
Correlation matrix. Is it?
No.
Then it was not like a built-in function for it.
No, I looked. I got this off of cross-validated, actually.
Oh.
I mean, down to the command.
Yeah.
I copied and pasted out cross-validated. I wish there were, but I don't know what you would see from this one. Okay, ggplot2. And if you are familiar with ggplot2, you will notice that I am skipping over the command qplot. I am learning to love not ever using qplot in my stuff now. So what is ggplot2? ggplot2 is where we get really, really good. So I mentioned before that dplyr is a way of thinking, of coding while thinking about data analysis. So you're breaking down your data analysis into different tasks. In ggplot2, we do the same thing, but we call them layers. So at first, ggplot2 can be kind of confusing. Let's say we want to analyze our iris data set, and we want to do a scatter plot. So we do ggplot, and we do our data. So ggplot2 is data frame specific. It focuses on the data set. We have this AES, which stands for aesthetics. And aesthetics just means how do we map data to something on the plot. So we are mapping the x-axis to the species and the y-axis to the sepal width. So we do this, and we get nothing. So what happened here? That's because we did not say what we wanted. We said we wanted species on the x-axis, we get species on the x-axis, we got sepal width on the y-axis, but we don't have anything because we didn't ask for anything. So here's where we start layering. Let's say we just want to plot points. Each point is going to be sepal width by the species. So there we go. This is a stroke plot. It does have its uses, but maybe you prefer a box plot. Box plot gives you the median, the first quartile, the third quartile, and some of the extremes. So instead of doing a point, we are going to do a box plot. So we substitute this geom point with geom box plot. So I'm not going to go into the relative virtues of box plots versus stroke plots. I just want to show you that you can substitute one for the other very easily by doing this kind of layered approach in ggplot2, just like you can in numbers and tables that you might do. You can do both. You can add points on top of this box plot. There you go. And we did it just with this plus command. And so really this is the power of ggplot2, is this layering. You define your aesthetics, and then you add layers of what you want on here. Okay, let's say we know that these are discrete measurements, and so when you have discrete measurements, this point might be 15 observations, this might be 20, we don't know. So when we do that, we want to jitter that. Well, that's easy in ggplot2. This looks really kind of hard to see, so let's bring these in a bit. So I add an option to this geom jitter, and so and now we start to realize the power of jitter. We look at clouds of points rather than points that are plotted over each other. So I don't know if you've encountered it before, but I did want to show you that it is possible to do this. And if you do a lot of scatter plots with discrete data, jittering is something to look into, and ggplot makes it easy. All right, let's do a scatter plot. Sepal width by sepal length. So we're going to do this plot 2. So we define plot 2 as ggplot of iris. The x-axis is going to have sepal width, the y-axis has sepal length. And let's add the points. There you go, that's your scale plot. Okay, we might suspect that this differs by species. So we can color this by species. And we do that by specifying in geom point, we want to, there's this AES command, aesthetics again, and here we're saying we want to match color to species. Again, British spelling, force of habit. I think the American spelling works now too. Okay, so this is nice, but let's say we have this wonderful computer, but we have this old crappy Xerox photocopier in our office and we need to make a whole bunch of copies of this. So instead of mapping species to a color, we map it to a shape. And that way we can get something that's reproducible on our dummy Xerox copy. I hope that's not the case, but sometimes it is, and I just wanted to show that species could be mapped to different kinds of aesthetics. And so really now we're doing a kind of grouped analysis here in ggplot2 that is kind of like the grouped by analyses we were doing in dplayer. So we can get fancy. So let's add a line. Let's add a line to these plots. Okay, So we've done a linear regression now. We don't know all of the details of it, but we did the least squares line fit into this whole thing. But wait a minute, doesn't this differ by species? And the answer is yes, it does. Excuse me. And so we add an aesthetic of color by species. And now we have, not only do we have 3 lines over here, but we have this nice legend that tells us what the different colors are. And hopefully you won't have to run this through your old dummy Xerox copier. This is nice, but it's not the only way to do it. You might want a different plot for each species. So instead of doing this aesthetic color by species, we might want to put in our points, put in a linear or a line through all of these points, but maybe we want to do these on different graphs. So then we have this facet wrap command that does the following. And there we go. We have different graphs. And so, the point I wanted to make here, you are probably not going to be able to go out and use ggplot2, but what I do hope you know is that you can separate hard tasks down into smaller chunks with this package, and that is its power. And the same with dplyr too. So all of these different little data analysis tasks, if you want to go back and tweak it, or you want to do like we did with instead of doing the color, we did the shape with the species, doing things like that, that's easy to do. What's hard to do with ggplot2, which is hard to do with another system called base graphics, which is built into R, which I did not show here. And it's hard with the lattice system in R, it's the other major competitor to ggplot2, is making these publication quality. So changing the tick marks and changing the fonts and adding annotations, that's hard in any language, but that's not what we're doing here. That's not the point of this talk. The point of this talk is to get you thinking in terms of data analysis while you're coding in R.
Does it naturally make the x-axis uniform, or is this a coincidence because it's a sample data set?
This makes the x-axis uniform. You can tweak an option, and if I needed to do that, I'll go look it up on cross-validated or R bloggers. Actually, Hedley Wickham has a very good, thorough website on ggplot. He also has a book that is now, and it's about to be printed in its 2nd edition, so don't go out and buy the book yet. Wait for the 2nd edition to come out. And it is very, very thorough, very detailed. It shows you some very good tricks. And it's things like that are hard. It's like, does this axis need to be uniform? Maybe in some cases and maybe not. And going and finding the option to tweak that is a pain. It's a pain in any system. So we're not doing publication quality. So we'll have the fully lowercase species and all of that. So finally, I thought long and hard about this. I decided to go ahead and show you linear models using R because it's basic statistical analysis is kind of the first thing we learn after averages and standard deviations. So I wanted to show you basically squares. So it's this LM command and this really odd command construction here called a formula in R. And formula is another one of those things that is central to R. A whole system we glossed over due to time. but it is, as you get into R, it is worth learning about. It is very powerful. It is kind of the way of taking the data frame that we learned about today and transforming it into the underlying mathematics, which is matrix algebra. So it kind of sweeps all of those details under the rug from us, so we don't have to worry about how do we code this variable? Is it dummy coding? Is it, all these weird little decisions to turn, things that we think about like SQL width and SQL length into, column 15 of this design matrix. So all of these details really are swept under the rug. And if you use R to any extent, you will encounter formulas, and it is worth learning about them. But we can't go too much into them here, we'll just see them. So, but what this says is the Y variable is SQL length. We are analyzing it by SQL width, and our data set is Iris. So what I'm getting to now is the data analysis. So we've visualized this, we've split these regressions into 3, and then we actually want to go in there and get the numbers. This is not grouped. This is just a demo. There's your y-intercept and your slope. So easy enough to fit a least square line to something. And this coef command for coefficients again gives you the same thing. But the summary command, this is a little odd here. We saw summary on data frames. It gave us a lot of information. Summary gives us a lot more information than just printing out the object here. If you've done any sort of stats class, this will look familiar to you. It gives you the residuals, it gives you the coefficients, it gives you tests of significance, if you're into that. R squared, whatever you want. Now I'm going to kind of break with what I wanted to do, or what I have been doing. And I'm going to use base R graphics because R has been around a very long time. I've been using it since 2000, and I think the S language has been around since 1983 or something like that. So people have had time to develop these base graphics. And so what they've done is they've created a plot command for these linear models to do diagnostics. So residuals versus fitted and QQ plot. If you don't understand what it means, don't worry about it, but just know that these are diagnostics and these are things that you will learn about in your statistics classes. And R has them in there, and kind of makes the analysis of linear models very easy. So I just wanted to show you that was possible in case you had done a statistics class. It's like, all hard to do is averages and off. What is it good for? It does linear models, it does generalized linear models. It does the whole 9 yards. If you want to do group linear models, again, you got this awkward do command. I just want to show you that it is possible to get the slopes of these lines and the intercepts. So I did want to show you that it is possible. This is a very goofy construct. I don't expect you to come up with this after going to this talk, but I did want to show you that it is possible to do a grouped linear models analysis to kind of go along with what we saw in ggplot2. I believe there is a package that makes that easier now, but I haven't looked at it a lot. It's called Broom for some reason. Anyway, this is still possible. That comes to the end of a very, really just 30,000 foot view of what R can do and how to go from, just getting some very basic data analysis very quickly. So are there any questions or anything you want me to go into or something that's confusing? Although, if you want me to go through this, then maybe another time. We'll exclude that from the questions, but anything else is fair game.
I got a quick question. I feel like my head is spinning right now as I try to install while listening. It kind
Oh,
of
boy.
worked. But, so you put some stuff on Git already, and I looked at it, and I'm
Yes.
trying to, like, go over some of the things maybe
Yes.
afterwards. Are you gonna do some more for the second? Because I thought it was really good. It's great to have something to kind of, I don't wanna call it homework, but kind of follow up on.
I hadn't
Yeah.
thought about it. Well, no.
I don't know how people feel about it.
I mean, I have thought a little bit about it, because there are some very good deep dives that can be done into ggplot2 and dplyr. And I think either one of those could be great talks on its own. Data frames or whatever, many of these can be talks on their own. We hadn't planned on doing it, but I thought it did cross my mind today that it would be a good idea. That's all I got for you.
Are there any books that you especially like? That would be
Most
good?
of my books are specialized books, but okay, there are a couple of things that presentation. So we did the demo. So there are a lot of YouTube videos. The ones by David Langer I thought were very good. So you just look him up on YouTube. He has the 5-part series that each are an hour and a half long on Intro to R. There's the John Hopkins Data Science program that we were talking about earlier. I thought they were very good. They do best practices, but they heavily involve R in RStudio. And they do things like this R presentation that I do, and Shiny Apps, which is putting R analyses on the web and making them interactive. So very good stuff. I mean, just very thorough, but it is, you gotta drop some cash on it if you want to get the most out of it. I think it's almost $450 if you want to go the whole way through and do the capstone, but you're gonna know R and you're gonna know how to analyze data. There's a lot more on YouTube, and other I know other classes are good too. As far as books, let's see, Modern Applied Statistics in S is the classic. It was written in 2003. It is a little bit dated, but it is very good. That is, blanking on their names, not Wilson Chambers. Blah, blah, blah. I cannot think of their names. Let's just look it up. You can see that it is a package. Venables and Ripley. Okay, that's really embarrassing. Venables and Ripley's Modern Applied Statistics in S. S, as I said, is the underlying language that R is an implementation of. There is a package that is actually, I believe it comes with R, but it can be updated through the package mechanism as well. And that hits everything. It even goes up through predictive modeling, but some of the sexier stuff like support vector machines I don't think are covered, but it does cover things like regression trees and things like that. I highly recommend it. I use it. I still refer to it. The ggplot2 book I mentioned, wait on it a few months and then it'll come out in the second edition. In the meantime, I believe Hadley Wickham has posted a preview of it in PDF format. So, just Google ggplot2 book. You'll probably even come across Hadley's website. Very good documentation. I I haven't seen any books on dplyr yet, but there are some good talks on YouTube on dplyr, and hey, I may even get one here sometime. But the talks on are worth going to. We had a talk here a couple of years ago by another now defunct data analysis group, which was very good, but unfortunately we didn't record it, so there's that issue. And then the rest of the books I have are really just specialized. Applied predictive modeling is good if you want to go down that road and want to use the Kira package. But poor Jeremy, I was thinking about this from the CIO point of view, and he said the book was incomprehensible to him. It's a technically oriented book, but it is very good if that's what you want. So it's by Max Kuhn and Kiel Johnson, who also authored the Kira package. But it's a different take from what we got here. It's much more advanced. There used to be a couple of good introductory books, Introductory Statistics with R, and Data Analysis and Graphics with R, but I haven't used those books in a couple of years. They may have updated them to be good. They were good 10 years ago, but they may have been updated, I don't know. I haven't needed them.
Good talk.
Thank you.
I'm
Enjoyed
glad that
it.
you showed the overlay of the graphs. I haven't
Yeah.
seen that before, so that's
Yeah.
really good to know about.
Yeah, I mean, that is the power of ggplot2, is that kind of mix and match, one layer at a time, break it down.
All right. Well, I look forward to the next one.
I'm gonna
Thank
post
you.
some of these books on the
Thank you.
Slack channel if you're part of that. If you're not, you can go to hackgreenville.com and join.
And I suppose if you think of questions after you get home, you can pose them on the meetup site as well.
Yeah.
Okay.
Sounds good.
All right, thank you.
Thank you.
See y'all.